Okay, so our goal is to sketch this rational function by hand. And remember, with a rational function, there's 4 different things that we're going to need to find before we can sketch this. We're going to need to find the end behavior, which is that ratio of leading terms. And so that'll be that a sub n x to the n divided by b sub m x to the m will be what we examine to determine the end behavior. Then we'll need to find what is my y-intercept. And we find that by setting or evaluating f of 0 equals whatever my y-intercept is. We'll need to find my x-intercepts if they exist. There could be many, there could be none. And we find that out by doing f of x equals 0 and then solve for x. And then kind of the 4th thing that we need, there's no order to these, we just need to find these 4 things. The last piece of the puzzle here is going to be finding any domain restrictions. So looking at our domain restrictions. And at that point, we're looking for removable or non-removable discontinuities. So that's kind of the roadmap. Okay, let's start out looking at the end behavior. Now, in this case, that ratio of leading terms is 3x squared over 4x squared. And what we've said is that if the power of the numerator is the same as the degree of the polynomial in the denominator, so the highest power of the polynomial in the numerator is the same as the highest power in the polynomial in the denominator, that they grow at approximately the same rate. What that causes us to do is we see that then that leads to a horizontal asymptote. So since m equals n, we have a horizontal asymptote. Go ahead and write it out. And then it'll be the ratio of the leading terms. So it'll be as if the x squareds cancel. And so that'll be y equals 3/4. And so that's the first piece of information, is that I know I have, not only do I not have unbounded growth, so my left and my end behavior are finite, but I know exactly what they approach. I know they approach a value of 3/4. Okay, then I need to find my y-intercept. Well, my y-intercept is the same that we did for polynomial, and for our linear, for our lines. And so all we have to do to find our y-intercept is evaluate the function at an x equals 0 value. And what that does, we got to go back to the original function here. And so instead of 3x squared, I've got 3 times 0 squared plus 5 all over 4 times 0 squared minus 3. Well, 0 times something is always 0, right? 0 times something is always 0, so those are 0. And so what I end up with is 5 divided by -3, or -5/3 for my y-intercept. Making some progress. So a little more to do. So now I'm going to take my x-intercepts. And to do that, I'm going to take my f of x, set it equal to 0, and solve for x. Well, that was, if I scroll on up just a little bit so we see, that was going to be 3x squared plus 5 divided by my 4x squared minus 3 equals 0. I sort of didn't even have to write that out because I know the first thing I'm going to do is multiply both sides of the equation by that denominator. And so I really only needed to set the numerator equal to 0 to find the zeros for these polynomials. Now, what do? I subtract the 5 over to the other side. Oh, what am I noticing? When I subtract that 5 over, 3x squared equals negative 5. I should finish this just kind of for the example. But now I do x squared equals negative 5/3. Now when I take my square root of both sides of this equation, plus or minus the square root of that, this is a complex number. Or imaginary. Which implies no real solution, which implies no zeros. And so there are no x-intercepts. No x-intercepts. All right. Last thing we're going to have to check out here is what are my domain restrictions. And so when I take a look at this this part 4 here, let me switch colors so that we can tell what we're working on. To find a domain restriction, what I have to do is I have to look for zeros in my denominator, right? Because it's still a rational function is a polynomial divided by another polynomial. So I won't have any square roots of negative kinds of restrictions on my domain. So the only restrictions that I can have in my domain here are divide by 0 restrictions. And so what I need to check for is I need to check to see, can I simplify this? If I can simplify it and any zeros cancel out, those become removable discontinuities and they're holes in my graph. If I can't simplify and the 0 is still in my denominator when I have a simplified form, then I have what's called a non-removable discontinuity, and it shows up in the graph as an asymptote, a vertical asymptote. Okay, so I take my denominator. First I take a look at my original function. And so I take f of x equals 3x squared plus 5. Divide that by 4x squared minus 3. And looking at that, nothing in the numerator can factor, which since nothing in the denominator is going to be identical to the numerator means that we can't cancel. The only thing that we could factor from the denominator would be like a 2x plus root 3 times 2x minus root 3 using a difference of squares. And that looks nothing like the numerator. So we can't simplify this. So we take the denominator as is, set it equal to 0, and start looking for non-removable discontinuities. So we just checked, we can't simplify it, so there are no removable discontinuities, no holes in my graph. So cannot cancel. Cannot cancel any zeros out of the denominator. Implies no removable discontinuities. Okay, so now we need to check for non-removable discontinuities. And I do that by saying 4x squared minus 3 equals 0 and solving for x. This time, when I add 3 to both sides, I'm going to get 4x squared equals a positive number. And when I take the square root of a positive number there, that's going to give me 2 real solutions. All right, so divide by 4. Getting ahead of myself there. Divide by 4, divide by 4. 4's cancel, which is why we chose that. X squared equals 3/4. Take the square root of both sides. And I'll get that x equals plus or minus the square root of 3 divided by 2. I have vertical asymptotes. At x equals root 3 over 2 and x equals negative root 3 over 2. All right, let's try to put all this together into a sketch. And then, of course, we'll check our sketch against the calculator. And so if I've got my sketch here, what do I have? I have that my end behavior is a horizontal asymptote at y equals 3/4. And so I'm just going to start, put a dot in or a line in there for 1, and then somewhere around 3/4, I'm going to dot in a horizontal line. Okay? There, my y-intercept was -5/3. And so my y-intercept, if I put in a 1, 2, -5/3 is going to be almost -2, right? So that's going to be -5/3. And that's where I'm going to hit the y-axis. And I have no x-intercepts. And I have vertical asymptotes at plus or minus the square root of 3. Plus or minus the square root of 3 divided by 2. All right, so I need a little bit of a feel for the square root of 3 divided by 2. I know square root of 3 is what? 1.7 something? Let's check that. Square root, oops, not y. Second, exit, bad, there we go. Second, square root of 3 divided by 2, nope, not what I wanted. Square root of 3 divided by 2. There we go, even better. Okay, so if that's 0.866, which I should have remembered from trig, that means that I have vertical asymptotes at plus or minus. And so that's square root of 3 over 2. And then that's negative square root of 3 over 2. And so there's a vertical line through here. And a vertical line through here. All right. Now, didn't say this when I was finding these, but I also need my multiplicities, right? And the reason I didn't talk about multiplicity on my zeros is because there were no zeros, so I couldn't have any multiplicity on my zeros because they didn't exist. But I should have talked about multiplicity on my vertical asymptotes, because there's only one copy of each of these zeros, so each 0 is multiplicity 1. And so there's only one copy of each of those zeros being multiplied together in the denominator. And so I like to put a little note down here, M1 at the bottom of my vertical asymptotes, because what that does is it reminds me of the behavior of my graph around those vertical asymptotes. Because remember, an even multiplicity asymptote, so it's kind of a reminder, even vertical asymptote. If I have a vertical asymptote here, an even multiplicity, if it goes up on one side, it goes up on the other side. If it goes down on one side of it, then it goes down on the other side of it. An odd multiplicity asymptote, so an odd vertical asymptote, if it goes up on one side of the vertical asymptote, then it goes down on the other side of the vertical asymptote. And so looking at this, there's only one place I can start my graph, and that is my sketch, and that is the y-intercept. And I know that it has to approach those vertical asymptotes and that it cannot cross the x-axis. Well, there's only so many ways that that can happen. And that's the only one. Now, those are both odd multiplicity asymptotes, which means that if I went down to negative infinity as I approached that asymptote from the left, as I approach this asymptote from the right, I'm going to go up towards infinity. And so I'm just going to sketch this out. Sketch this out as kind of a smooth transition between those two. And then same thing, as I approached that asymptote from the right, I went down to negative infinity. And so this is an odd multiplicity asymptote, so I must approach positive infinity as I approach that asymptote from the left. And so I'm going to have a sketch that looks something like that. And so there's my 3/4 horizontal asymptote, my 2 vertical asymptotes, my y-intercept, and my what I have to draw in the middle. That there was no other choice. All right, well, now let's find out if we actually did a decent job with this sketch. All right, so I got to put parentheses around the entire numerator so that the whole thing's in the numerator. So I have 3x squared plus 5. And then I got to divide, then I put parentheses around so the whole thing's in the denominator. And I'll have 4x squared, then minus 3. And for my window, yeah, I thought I had something crazy for my window. Let's just do a negative 10 to 10, and we'll adjust it kind of as we need to, taking advantage of the touchscreen on this thing. All right. And if I graph this, well, what do you know? That looks pretty good. Because I've got my 2 vertical asymptotes, right? And if I keep going out, you can see that horizontal asymptote, I mean, it almost looks like a straight line if I keep going far enough out, right? That's very far out, but if I keep going far enough out, that looks like a straight line. And that was, well, it's hard to tell on this, but that looks like about 3/4. That's not a half bad sketch for the information we had. All right. I hope this helps us in sketching our rational functions.